studying iterated modular symbols was the theory of classical modular symbols, which in turn comes from analysis of the Manin transform, basically. Combination of analysis of Manin transform and various functional equations that we get out of it. But there was another motivation, and actually the theory of iterated modular symbols is a kind of common generalization of two subjects. One is classical modular symbols, and another is multiple zeta values, which I will explain today, and also a part of this story. And then tomorrow will be dedicated more or less entirely to the remaining part of the story of iterated modular symbols. Okay. So multiple zeta values. What is this? The basic definition is this. It is an infinite series family of numbers which are denoted this way and defined in this way. And so Mi will be positive numbers, and for convergence, positive integers. And for convergence, we need the last one to be at least 2. So this is the definition. And of course, a special case is when k equals to 1, so we get just the usual values of zeta at integers. And I told you that one of the uses of classical modular symbols is evaluation of certain values of certain L series at certain integral points. So this is, of course, the classical case. And we have a very general problem understand the arithmetics of these numbers. And of course, what we know classically for zeta is that if we are considering values at even points, then it is essentially some rational number multiplied by the respective power of pi. This is, I think, Euler again. And Bm is kind of normalized Bernoulli numbers. But the odd ones are more or less still a complete mystery. Conjecturally, they are totally new transcendents, new in the sense that there are no relationships between them and anything else that we know. And so the more precise form, so what kind of arithmetics we can expect from something that we think is transcendental? Okay, at least relations between them. So more special form of this problem. Try to understand, say, polynomial relations with coefficients in Q. So one can ask coefficients in Q bar or something like that, but at the moment we have nothing to say about that. So try to describe polynomial relations with coefficients in Q over Q for between these numbers. And what we can do, describe some polynomial relations, construct them. And even this positive part is quite funny. There are several unexpected twists in this story, and I want, in order to motivate what I will be doing next, I want to explain how we do that. But before this, I want also to say where all of this appears, where all these numbers appear. Well, I think Euler just introduced them for the fun of it. Euler and then the second person in the history of mathematics, Srinivasa Ramanujan, were absolutely great inventors of infinite, what I call infinite identities. I don't know whether there is a general name for it. But I mean, if something is finite, some polynomial identity, you just sit and calculate. But they developed an art, high form of art of producing identities between power series. And I think after Ramanujan, probably only Don Zagier was able to do something comparable, but probably nobody else. This art is somehow lost. So Euler started for the fun of it, then it was pretty much forgotten, and then in the 80s and 90s, these numbers appeared in work of Drinfeld about quantum groups, work of Kontsevich about quantization, more general quantization. If you have a C infinity manifold with, say, symplectic structure, then you want to quantize it. It's a very definite mathematical problem. When he solved it, he got these numbers. This line of thought was recently reappeared in Kohn-Marcoley papers, so that these numbers are related to what you regularly get in various types of Feynman integrals treated in theory of perturbation, so that actually integrals are series, and they reappear here regularly. And as I said, Don Zagier, who was motivated by purely classical considerations, he loves arithmetics, and he can do things which Euler and Ramanujan were doing, and he invented several beautiful things around this story. Okay. So now how do you get relations? Well, I will explain two ways of doing it. And the code word is shuffles. And the first way is getting relations using shuffles with repetitions. And, well, you do a very simple-minded kind of producing infinite identities, and you will see what I mean very soon. So the simplest case, so let's take two usual zeta functions, values of usual zeta functions, and P and Q. So it is a sum like that, multiplied by a sum like that. Okay, everything is everything absolutely converges. So P and Q are supposed to be at least 2. And okay, obviously, you can take just term by term product and then sum. And there is the first sum over those pairs where n1 is less than n2. Then the second sum when n2 is less than n. And then the third sum when n2 equals to n. n1 equals to n2. And this is obviously zeta pq, and this is zeta qp, and this is zeta of p plus q. So very, very simple-minded. But you have some bonus. If you take, say, p equals to q2 equals 2, you will get formula for z22. It will be zeta of 2 square minus zeta of 4. And you know this by Euler, and so you know explicitly this. It's some rational number multiplied by a fourth power of pi. Now somewhat more sophisticated case, but if there is anything more sophisticated, it's pure combinatorics. And it involves combinatorics of shuffles. And what kind of shuffles you get here? So you try to multiply, say, one multiple zeta value by another multiple zeta value. And you get something like that. Well, now I have trouble with notations, but okay, something like that. N1 power P1 and K power Pk, and then N prime 1 power Q1 and prime L power QL. And then, of course, what I want to do is, so here, these are in the increasing order. These are in increasing order. And in order to get some combination of new multiple zeta values, I have to reshuffle every particular instance of this term in such a way that n's and n primes were in increasing order. And if some n here equals to some n prime here, I count it once, but then, of course, I add the respective p's and q's, right? Should be clear what do I do. And so basically the result is that I get sum of zetas. And now, as is more often than not in combinatorics, the whole problem is to write down precise notation and convenient notation. Okay, so the sum will be with respect to shuffles. What are shuffles? Okay, I have p, k, n's and ql, these things, and I get out of them another sequence of length, generally k plus l, but perhaps a little bit less, and this is uniquely determined by these n's and n prime. So what is a shuffle? A shuffle is a map showing to which place each of these ni's gets. So I'll take, and now there is a categorical problem, although you probably do not recognize it. What is disjoint sum of two sets which have common elements? Okay, I will not do anything about general explanations, but I'll put prime near. I will imagine that I have two different copies of integers. So I will get disjoint sum. And then I map it from here to here. And of course, inside each group, S must be increasing. And here it must be increasing, strictly increasing. But otherwise, they can get at the same place. That is why it's called shuffle with repetition. Each such S. So I will have some terms corresponding to each such S. And then here, there will be some kind of arguments depending on this shuffle. And I leave to you a pleasant exercise to produce notation and to describe exactly what sits here. Okay? So the net result is that we get essentially quadratic relationship. Left-hand side is bilinear in zetas, and right-hand side is linear in zetas. So we get relations of degree 2. So formally they are not homogeneous, but actually they are homogeneous if you introduce the grading in a nice way. They will be homogeneous with respect to grading in which the degree of such a multiple zeta value is just the sum of mi's. And this is called, I think in the literature, it's called the depth of the corresponding zeta value. So now you can be a little bit more sophisticated and pose a question. You have a polynomial ring generated by symbols, formal symbols, say I'll use capital zeta for these formal symbols. Then I'll take the quotient, and then I, of course, grade it as above. And then I take a quotient by the ideal generated by these shuffle relations, these repetitions. And then I can ask two questions. I have, of course, a homomorphism like that. And then I can ask whether there is something in the ideal, something left. And what is, for example, degree of component of dth component? What is the dimension of the dth component here? Well, it turns out that it's certainly not an isomorphism. There are more relations than these shuffles, and for very, very funny reason. And but you can try to answer this question for yourself. Don has concocted a conjecture telling what happens with dimensions when we take into account all relations that we can construct. But it's a little bit too late to ask this question, but at least you should know what to ask. Okay. Now, it turns out that to get other relations, one can proceed in a very similar way, but starting not with Dirichlet series, but with integrals. Again, let's start with the simplest case. Consider just usual zetas. The integral representation was again known to Euler and was totally forgotten, it seems, until Drinfeld and Kontsevich. Here is the answer. So it is a multiple integral, but the integration should be taken from inside to outside, whereas the numeration of the respective variable goes in the reverse direction, reversely. Okay, so this is a function of upper limit. You know what function it is, I hope. You multiply it now by dtm minus 1 divided by tm minus 1. Put upper limit like that. So on. Sorry. To confuse due to 1. Now, why this is so? Let's see. So if you start with this inner integral, you can just consider the geometric series and integrate and so you integrate, but upper limit is here, so the answer is okay, now you integrate by now what you put here to do the next term. You integrate from 0 to Tm minus 2. Okay, when you divide by Tm minus 1, you get here Tm minus 1 power k. But then you integrate once again, and the power remains k plus 1, but instead of k plus 1, you have k plus 1 squared this time. And since you repeat this story m minus 1 more times until the upper limit becomes 1, so at the very end, you get exactly this. And this is, of course, the value of zeta, right? And this was the simplest case. And the same reasoning shows you the integral expression for the whole multiple zeta. And what happens is this. I will now use a more sparse notation because you see the pattern now. Again, the point is that you start from the right-hand side. This is why in various papers people select various order of m's. I could have changed the definition and put all m's from the right to the left at the very beginning, but okay, I have chosen this one. The price is that I will have to do here in the reverse order, starting from mk. And all in all, there are mk terms. The last one uses the differential form dt1 minus t, and the former ones dt1 over t. Then there will be the group of mk minus 1 of the same structure, and so on, until you end by m1. And of course, you should number all these t's which are intermediate and will vanish anyway. You should number them consecutively, right? So you have an integrated integral. It is useful to imagine that you are integrating over the simplex. What is the total dimension of this simplex? Okay, it is our depth up there, which is the grading. We already had this grading. Where was it? This one. And it reappears here. So this is the simplex whose dimension equals to depth of our number. And we are integrating a differential form, which is a product of these forms, and which depends on M1 or MK, M1 in this way, over this simplex. So several dt's over t's, then first stop, and we have dt over 1 minus t. Then again, several dt's over t's, again, 1 dt over 1 minus t, and so on. The proof is just by induction, similar to what we have done here. What is what? Well, you have as many integrals here as the depth of my zeta, that is mk plus mk minus 1 plus m1. Okay? These t's are variables that enter in the complete description of this form. Here we had t1, t2, t3, tm. Then tm plus 1 will be, again, correspond to the form dt over t and so on. So these t's are just variable of integrations. And instead of writing the integral, I can write the integral over exterior form, if you wish. It will start something like that. Well, here, a nasty problem of sign arises, depending on how you normalize signs, and I will not say anything about it in the same way as I didn't say anything about the problem of taking disjoint union of the same set with itself. But anyway, it depends on the agreements you make. How do you reduce an integral of exterior form to the iterated integral? I will not say anything about it. Some sign depending on this combinatorics. And this is the simplex over which we integrate this exterior form. Any more questions? Yeah? Yes. This is a different story. There are interesting developments about complex numbers, and one can write down functional equations, and something about it will be clear from my following exposition. But right now, I want to consider only these numbers. Okay, so we have this integration, and the funny thing is that you now can get new relations corresponding to shuffles without repetitions. So you just play the same game. I will try to produce the simplest example. Let's try to treat zeta p by zeta q in the same way, but using integral representation. So you will get integral of this form over the simplex of dimension p multiplied by the integral of this form, well, plus minus everywhere, over the simplex of dimension delta q. And of course, in totally the same way as we treated infinite dimensional lattice simplices, so to speak, we can treat this one. So this product is a union of simplices of dimension p plus q. So t's that enter here, we just add to the t's that enter here, and then rearrange them in the order, this time decreasing, in the decreasing order. Well, there will be, the funny difference between the case of shuffles without repetitions is this. if two n's repeat, they produce a new term in our sum. But if two t's repeat from the left-hand side and from the right-hand side, they produce a phase of the simplex. And the phase is smaller dimension. And the integrals will be 0 anyway. So you can forget about repetitions. And therefore, the net result is that you will get the sum over shuffles without repetitions, which will be now bijections. This is the meaning of absence of repetitions. There will be now bijections. And of course, increasing. Or non-strictly, but increasing. So this is the meaning of this decomposition. We just, for any t's and t primes, we put them in the correct order, and the union of these t's in the correct order is by definition this p plus q. So it is numbered by s, and s are shuffles without repetitions. So this should be 1-to-1. Okay, and what is inside? Well, each particular story, each particular integral will be reshuffled. So what sits inside? Each particular integral will be reshuffled product of this type. Sign will depend on the shuffling because it is exterior form. But it's clear that the structure of the differential form will be the same as it used to be, only here we have only one form of the type dt divided by 1 minus t, and here 1. So all in all, there will be 2. And therefore, we will get some sum of zeta values depending on 2 arguments. Which exactly, again, an exercise for you. This is exercise in combinatorics, but beautiful combinatorics. Okay, exercise, introduce notation, and write everything properly. Now, what is the funny thing is that even in the very, yeah. Sorry? Delta p cross delta q, but it is a union of simplices of dimension p plus q, and these simplices are numbered by shuffles. Therefore, the integral will be the sum. Okay? And what is funny is that even in the simplest case, when you are multiplying zeta 2 by zeta 2, you get something different from this relation, even in the simplest case. Why? Well, that's very funny. So you have dt divided by t, dt divided by 1 minus t. This is the first form. And then say dτ, I omit the indices. And then in the first form, in the second form, dτ divided by τ, and dτ divided by 1 minus τ. And then I'm somehow reshuffling, t's and t's in such a way that they are in the decreasing order. And you see that the terms that appear here correspond to the following order. There are some terms which correspond to the following order. We put this here. Consider the simplex where this sits here. And what kind of multiple zeta you get in this way? Well, this is the group of length 3, and this is the group of length 1. And so you get with some coefficient, the value zeta 1, 3. Whatever else you get at the right-hand side, well, you can check that it does really appear with non-zero coefficient. And whatever you get else in the right-hand side, this was something that you didn't have up there and couldn't have up there, because zeta 1 doesn't appear. Zeta 1 diverges. So you really get new relations. That's very funny. But at least then you can add to the, so add new relations. So this was series shuffles. And here you get integral shuffles. And you can now ask, perhaps now this becomes an isomorphism. The answer is no, still not. There is one more way we can produce relations, and this is this. I have had to exclude the case when mk equals to 1 up there because the series diverges. And similarly, I have to exclude the integration where dt over 1 minus t appears at the first step, because then the integral will diverge because of logarithm of 0. So what to do with that? Okay, there are various ways to regularize divergent series or integrals. One can produce one way to regularize them. Introduce, so the logic is this, somewhat convoluted. So the third way of getting relations. Choose a way to regularize our integral, a regular procedure, so that we can allow, well, for example, the case mk equals to 1, probably something else. Imitate the reasoning with shuffles for the regularized values. For, well, ordinary plus or convergent plus regularized values. And then look at the whole set of relations you get and try to eliminate the values that didn't appear before. Try to eliminate the values that are new and obtained only because you made a regularization. Eliminate the new values from relations. It turns out that in this way you get again some new relations. And that is all that we understand and actually assume that there are no more. So conjecture, but nobody knows how to really try to do something about it. So after these 3 steps, we know all relations. So this is a remarkable story, which seems to be some very particular and idiosyncratic part of combinatorics or whatever. But since it appears in quantization and similar things, it is an interesting story, and it is intrinsically very beautiful. Okay, now I want to relate this story with modular symbols. And then I'll start describing the common generalization of multiple zetas and modular symbols. Okay, what kind of geometry is behind iterated integrals of that type? We have two differential forms, dt over t of one variable and dt over 1 minus t. If I imagine that t is a projective coordinate when I find coordinate on a projective line, these two forms have three poles at t equals to 0, t equals to infinity, and t equals to 1. So we have t equals to 0, t equals to 1, and t equals to infinity. T equals to infinity on, okay, this is actually a real projective line, but it's convenient to consider complexification on P1C. And our iterated integral path is between 0 and 1. But our forms have logarithmic poles at the ends. Okay. Now, if we return to our picture of upper half plane and cusps, so real rational points, including infinity, it's one of the classical facts of the theory of modular groups and modular forms is that we can uniformize this P1 of C with 3 points as a result of mapping H to P1 of C. And what kind of mapping it is? Well, we take everything modular one of two congruence groups. It can be gamma 0 of 4 or gamma of 2. Let me remind you the definition. Gamma 0 of 4 is a subgroup here consisting of the matrices A, B, C, D, such that C is divisible by 4, and gamma of 2, you can take any one of them, whatever you wish. The same matrices with conditions B and C even. And these 3 points become exactly cusps. So 0, 1, and infinity are images, so cusps on our modular curve, that is, images of rational points including I infinity. And if you take this particular path from 0 to infinity and lift it up there, you'll get one of the geodesics depending on the normalization. For example, you can get the geodesic which was crucial in our treatment of Manin transform from 0 to infinity. Or if you wish, infinity to 0. It doesn't matter much because you can slightly change this phi. Okay. So instead of this geometry, I will be considering this geometry, but of course I need forms. I have also forms. So downstairs I had dt over t. What does it become upstairs? Well, it becomes an Eisenstein series. I will not give a precise definition here. It becomes an Eisenstein series, which is regular inside H, but has kind of logarithmic singularities up there. Or rather, Eisenstein series multiplied by dz, because it is one form. So basically, this will be a weight 2, modular form of weight 2 for one of these groups, whatever you choose. Well, and the same happens with dt1 minus t. Another Eisenstein series multiplied by dz. And so if instead of doing iterated integration here, I will be doing an iterated integration here, I will be exactly in the situation I was suggesting to consider with a very particular modular group, gamma of 2 or gamma of 0. Okay. And this is another motivation for considering such iterated integrals. And we will see that whenever we are looking at the sufficiently general context for this story, many things that look very peculiar, shuffles and quadratic relations and things like that, acquire an extremely beautiful and general, actually, geometric, differential geometric, and so on interpretation. And so finally, I start earnestly the story of iterated modular symbols. But the first part of this story is, of course, much more general. So part one, iterated integrals of homomorphic one forms on a general Riemannian surface. And it is a part of Chern's theory of iterated integrals on C-infinity manifolds, which is extremely beautiful, and I recommend you to study it a little bit. It leads us to a totally different subject matter, essentially homotopy theory of C-infinity manifolds and so on. I will be treating very particular specific properties of this particular case. Okay, so some formalism. So I will consider a connected Riemannian surface. If you wish, you can imagine upper half plane all the time. Doesn't matter much. The main difference is that generally it can be not simply connected, but I will omit the particularities of this case because H is simply connected anyway. So then I will imagine a family, a finite family of holomorphic one forms. The forms like that on the compactified modular curve have poles of logarithmic type, but I will be considering holomorphic case until very end. Then I will say a few words about how to deal with logarithmic poles. And here, this set is just pure bookkeeping device. So a finite set, which is a purely bookkeeping, nothing special. The point is that I do not want my forms to be ordered. If I said omega 1, omega n, you would implicitly assume that there is the first one, the second one, and so on. I don't want this, so it will be just numbered by. Okay. And then, what is quite important and not obvious at all why it should be done, I will be considering not individual iterated integrals like up there at the very upper line of the upper blackboard, but I will be considering a generating series for all of them together. It turns out that all this combinatorics, which is not really very nice, becomes very well packed if one considers iterated integrals as coefficients of a formal series in non-commuting variables, in free non-commuting variables. So there will be as many formal non-commuting variables as my forms. The family will be numbered by the same set. Free associative non-commuting formal variables. And this means that my objects I will be considering will lie in the ring of such formal variables generated by this, in the ring of formal series generated by these variables. So I will start with producing just one form, so to speak, the generic form spanned by these omega v's. And I will choose an integration path. So it will be a map from 0, 1 to u. But actually, since I will be integrating holomorphic forms, the integrals will be invariant with respect to parameterization and even to the homotopy with fixed ends, so it doesn't matter much. But at the beginning, okay, let's consider such a path. Such a path. And then the basic definition is the total iterated integral of this family omega v along gamma This is defined as a formal series here, so it's not a number. And then essentially I'm writing what is up there only with abstract forms. So it is here, a formal series. Or else, I will just use another notation for the same story. If gamma 0 is a point A in X, and gamma 1, I will denote it not by B, but by Z, implying that I will be treating the upper limit as variable. Then I will write the same integral in a different notation. So integral from A to Z, total iterated integral from A to Z. And here, instead of telling exactly what is the path of integration, I will just repeat that up to homotopy, it doesn't depend on anything except of ends of integration. And so I will write ends here from A to Z and rename the t's that were t coordinates here. I rename just by zi's, which will be which will be points on X. So and this will be my main object, this iterated integral, total iterated integral. And this notation is slightly less precise than this one, but it's more intuitive, so I will be using it. Well, what I'm saying is this. If it's not simply connected, then in addition to this notation, I should say, and I specify a homotopy class of a path from A to Z up to homotopy up to with fixed ends. If it is simply connected, then I will not specify it. Doesn't matter, just choose one path and go along, Z will be along this path. This is all implicit in the notation, but I prefer this notation because it's somewhat more intuitive than this one. This one is more precise. Okay. Okay. Well, there is not much time to do more job today, but just a little bit. Okay, so the first proposition is this, that if I take this series, this formal series, and we'll consider it as a function of the upper integration limit, so it will be an infinite formal series, but coefficients will be holomorphic functions on my Riemannian surface. And then I take the differential with respect to z. So coefficient-wise, my AIs are constants with respect to z. Okay, and the statement is that is just multiplication of omega from the left to JAZ. This is linear term in A's. All functions and constants commute with A's. By definition, they are central. And this is very easy. Just when you integrate the first term here is replaced by omega of z here, and here z's are renamed, and that's it. Yeah. What is what? Big omega is here. It's a differential form with coefficients in our formal series with non-commuting A's. So when I'm integrating, I'm treating AV as constant with respect to integration and differentiation over C. How do I what? Just coefficient-wise, you are treating forms as forms, and you are treating non-commuting coefficients as non-commuting constants. Okay, so this is the first, very easy. And intuitively, I am saying that JZ omega is a horizontal section. Can I have 3-4 more minutes just to finish this proposition? Horizontal section of the flat, multi-section if you wish, of the flat connection on X with the connection for which is just D with respect to Z minus left multiplication by omega. Well, this all should be in inverted commas, of course, because the fiber is infinite dimensional. The fiber consists of this series. But okay, it's a trivial fibration with infinite dimensional fiber, and I can define the left connection in this way. And then this equation just says that this is a flat connection. And second, if I have a simply connected neighborhood of A, so of lower limit of A, then GAZ omega is the unique flat section which at this lower end equals to 1. Otherwise, of course, you have some kind of multivaluedness connected with fundamental group, if there is a fundamental group. It follows that any other solution, so any other flat section of the same connection can be uniquely written as some constant multiplied by GAZ omega, whereas constant, of course, is a formal series with constant coefficients. So from where do you multiply is very essential. They are not commuting. And therefore, in particular, you have the following which is a non-commutative iterated analog of just the formula for usual integrals, which says that they are additive with respect to paths of integration. And if you look at the linear in AV terms of this story, then we will see that at linear terms, this is exactly what this proposition is saying for linear terms in AV. But if you didn't treat all iterated integrals together, you would have instead a long, long infinite series of negativity. And this is, I would like you to remember this formulation, because it will turn out that other simple or not very simple things in the usual integration acquire a similar generalization in the iterated case. And this is very easy. I suggest you to try to do it as an exercise. Thank you.